A very good morning to Dr. Shari and Dr. Hakima. My name is Xiu Juan, and today I'm going to present my final year project 2 report. My final year project is titled Impact of DG on Voltage Profile and Power Losses for 3311 kV PPU Bakar Batu and PPU Century for Johor Bharu using PSCAD software. This presentation will consist of the introduction, problem statement, objective, scope, literature review, methodology, result, and conclusion. A traditional power system using fossil fuel and function to transmit the electricity over a long distance to reach the consumer. However, the burning of fossil fuel will cause the climate change due to the emission of the greenhouse gases. Recently, Malaysia government is aimed to reduce the greenhouse gases by 45% in 2030 with the use of renewable resources to reduce the dependency on the fossil fuel to generate electricity. Therefore, distributed generation DG mostly come from the renewable resources able to resolve the global warming issues. Since implementation of DG is getting wide throughout the years, so it is important to figure out the impact of DG to prevent negative issues occur on the existing network after the DG connection. This research will focus to evaluate the impact of DG in terms of voltage profile and power losses on Malaysia's 3311 kV distribution network. One of the most common problems that arise in the radial distribution system is maintaining the load voltage profile. The voltage will decrease from the front of the feeder to the end of the feeder caused by the line impedance on the cable. Next, in the radial distribution network system, the power losses will be higher as the current flow through the load is higher. Also, most of the study investigate the impact of DG on the radial distribution system based on the IEEE bus system and also US network system. So it's crucial to figure out the impact of the DG in terms of voltage profile and power losses in Malaysian network. The first objective to conduct this research is to model and simulate a 3311 kV network system using PSCAD simulation software. Next is to investigate the impact of DG on voltage profile and power losses. The third objective of this research is to analyze the ideal location of placing DG for minimum voltage drop and minimum power losses. The limitation of this research first is only focused on the 3311 kV medium voltage distribution system in Malaysia. Next, the networks at PPU Bakar Batu and PPU Century Johor Bharu is chosen as a reference in this study. Also, PSCAD simulation software is used to model the test system and obtain the simulation result. Lastly, there is no specific of DG will be used to implement the distribution network. Based on the previous study, some information and knowledge regarding the DG and its impact of the voltage profile and power losses is being clarified. For example, there are different notations of DG are using in different countries, like embedded generation used in the US, dispersed generation is used in North America, and decentralized generation is used in Asia and Europe area. Also, DG is a clean and pollution-free power generation, which is able to produce power in the range of 10 kW to 10 MW. DG is a type of new technology that can satisfy the high demand for energy by supplying electricity to the consumer during peak load hour. Next, the connection of DG can maintain the load voltage profile stability within the limit, which is 0.95 per unit to 1.05 per unit. The location of DG placement will affect the power losses when DG contribute both real and reactive power to the distribution network. The method used to conduct this research are first, collect a 3311 kV medium voltage network from TMB and is considered as a reference network for this research. After that, the distribution network based on PPU Bakar Batu and PPU Century are modeled into PSCAD software. Next, the power flow and the load voltage profile are observed and recorded. After that, the comparison for the case with and without DG connection is carried out to determine the impact of DG on voltage profile and power losses. The test system for PPU Bakar Batu consists of one generator, two transformers, and a total of 13 bus bars, which consists of different load values. Meanwhile, the test system for PPU Century also have one generator, two transformers, and 10 bus bars. In the PPU Bakar Batu test system, the buses 11 to 30 represent the connection of the PPU to the SSU south key through a long cable by considering the line impedance. However, in PPU Century, bus 10 is the SSU Sky 88 connected by a long cable. This is the schematic diagram for the PPU Bakar Batu that modeled in PSCAD software when a DG is connected to the bus 13 of the network. The appearance power of the load need to convert into real and reactive power in the simulation by using the formula of the P equal to S cos theta and Q equal to S sin theta. The power factor used in the simulation is 0.9 as TMB requires the consumer who taking the supply of the 3 kV or below to maintain the power factor at 0.85 to 0.95 to avoid the power surcharge penalty. The power flow and the voltage profile are recorded and observed using the multimeter in the simulation software. The voltage profile are measured in per unit, which the result need to be achieved the range of 0.95 to 1.05 per unit as determined by the electric utilities. This is the schematic diagram for the PPU centrally that modeled in the PSCAD software. All the simulation process is same as the simulation in the PPU Bakar Batu. In an ideal system, the total power that generated by the generator should be same with the total power that received by the loads. The power losses can be determined by the total power that generated by the generator and the DG deduct with the total power received by the loads. So the difference of the result will be the power loss of the distribution line. The transformer losses is considered in the simulation as the power is reduced after pass through the transformer. This is a network characteristics for PPU Bakar Batu and PPU centrally. The line impedance is only considered for the cable that connected to the PPU to SSU as the distance between it is longer than the load strip connected to the PPU. Several cases have been conducted to analyze the impact of DG on the existing network before and after the connection of DG. There are 3 different cases to be analyzed at PPU Bakar Batu, where case 1 is without DG connection, case 2 is different DG sizes connected at bus 2, case 3 is different DG sizes connected at bus 13. Another 3 cases conducted at PPU centrally are case 4 without DG installation, case 5 is different DG sizes connected at bus 2, case 6 is different DG sizes connected at bus 10. Based on the result analysis in PPU Bakar Batu, in a normal distribution network system, the voltage at buses 11 to buses 13 are dropped below the allowable limit of 0.95 per unit to 1.05 per unit. After the DG connected to the feeder front of the network, which is the bus 2, the load voltage at bus 1 to bus 10 are maintained at 1.0 per unit and the bus voltage at buses 11 to 13 are increasing with the increase of the DG size. However, the improvement of the DG is still not satisfied the minimum limit of 0.95 per unit. When a DG is connected at the bus 13, which is known as the feeder end of the network, the voltage load at the load is overcome and have a great improvement on the voltage profile on the buses 11 to 13. It is obvious that when the size of the DG increases from 15 MW to 50 MW, the voltage improvement is increasing. The increase of the voltage profile is within the allowable voltage constraint. Next, for the analysis of PPU centrally, before the DG is injected to the network, the buses 1 to 9 are maintained at 1.0 per unit, while there has a voltage drop at bus 10. When a DG size of 50 MW, 25 MW, and 40 MW are connected to the bus 2 of the network respectively, the voltage at bus 10 is reduced 0.002 per unit. Therefore, if the DG is injected to the feeder front of the network, they will have a voltage drop at bus 10 compared to the case without DG installation. Since DG installation at bus 2 does not show an improvement of voltage profile at bus 10, so another case, which is a case 6, is carried out. The load voltage at bus 10 is above the minimum limit of 0.95 per unit before the DG is installed into the network. So there is no necessary to install a DG on the network, but the installation of DG can overcome the voltage drop at bus 10. So from the experiment result, it showed that there has an obvious improvement of voltage profile at bus 10 when the size of the DG increased from the 15 MW to 50 MW. Hence, the voltage drop at the network are overcome after DG is connected. Next, for the analysis on power losses, only active power loss is considered in the analysis. When there is no DG installed at the PPU Bakar Batu network, which is under the case 1, the power losses is recorded at the highest, which is 2.2908 MW. However, when the size of the DG is injected to the bus 2 is increased from 15 MW to 50 MW, the power losses at the system is decreased gradually. The result has shown that there has a significant reduction of the power losses when the largest DG size, which is 50 MW, is installed to the bus 2. When DG is installed at the feeder end of the network of PPU Bakar Batu, which is the bus 13, the power loss at the system is decreased, but the reduction is not significant. When the largest DG size, 50 MW, is placed at bus 13, it recorded the highest reduction in the power loss, which is from 2.2908 MW to 1.2374 MW. In the analysis of the PPU centrally network, without the DG connection, the power losses is 1.2195 megawatt. The power loss at the system decreased gradually when the size of the DG injected to bus 2 is increased from 50 megawatt to 50 megawatt. The result shows that there has a significant decrease from 1.2195 megawatt to 0.7917 megawatt in the power loss when the largest DG size 50 megawatt is installed at bus 2. And there we can conclude that the installation of DG into the network, which is at the feeder 2, feeder front of the network, it can cause the power loss at the system reduce. The power loss as a system decreased, but the difference is not significant when the size of the DG is increased from 15 megawatt to 15 megawatt are installed into the network at bus 10. In this case, the largest DG size, which is the 50 megawatt, is placed as the bus 10 recorded the highest reduction of power loss, which is from 1.2195 megawatt to 1.0323 megawatt. Based on the simulation result, it showed that the injection of DG able to improve the voltage profile back to 0.95 per unit at bus 11 to 13 at PPU Bakar Batu. Also, the injection of DG has overcome the voltage drop at bus 10 of PPU centrally. The placement of DG is able to share the responsibility with the main generator, which enable the load to meet the demand with the substation. Hence, the voltage drop will overcome and voltage at the load will going to increase as DG can support the load demand. After DG is injected into the bus 2, which is the feeder front of the PPU Bakar Batu, the power loss is lower compared to the DG installed at the feeder end of the network, which is the bus 13. However, the power loss reduction at the feeder end, which is the bus 10 at PPU centrally, is lower than the feeder front of the network, which is the bus 2. Therefore, it can show that the location of DG is important as need to analyze before the installation of DG. In the analysis of PPU Bakar Batu, the power losses reduction when 50 megawatt is installed at bus 13 of PPU Bakar Batu is 43.58%. When 25 megawatt and 40 megawatt DG is able to reduce the power losses at 45.2% and 45.85% respectively. The power losses is reduced 45.98% when the largest DG, 50 megawatt, is injected into the network. At PPU centrally, the power losses reduction is 14.29% when the 15 megawatt DG is connected to the bus of the network. The network is achieved 14.61% and 15.10% power losses reduction when the 25 megawatt DG and 40 megawatt DG is connected to the network respectively. The highest power loss reduction is at 15.35% when the largest DG size 50 megawatt is connected to the bus of the PPU centrally. In conclusion, the optimal location for DG connection on PPU Bakar Batu is at bus 13, while the optimal location for PPU centrally is at bus 10. After the DG is connected at bus 13 of the PPU Bakar Batu, the voltage drop is reduced and DG is able to improve the voltage back to 0.95 per unit. While in PPU centrally, after DG is connected to bus 10, there is no voltage drop compared to the normal network after DG is connected. In both substations, the minimization of power loss are achieved. So that's all for my presentation. Thank you.